Hi everybody, my name is Christine Flood. I'm here to talk to you about Shenandoah, an ultra-low-pause-time garbage collector for OpenJDK. So the benefits of garbage collection. I had somebody that once talked to me about how it was like having an omniscient housekeeper that would come into your house and get rid of all of those things you were never going to use again, so that all you would know is that you now have a lot more space and the stuff you want to get to is a lot better organized. You don't have to deal with memory problems like premature freeing of objects or safety. You have a lot fewer memory leaks. You have better cache page locality, less memory fragmentation, and in my mind, the most important one is you have fast pointer bump allocation. Now, fast pointer bump allocation is huge. It gives you the ability, rather than having to try and find the right spot to put something, every thread has a thread local allocation buffer, and they can do a very quick allocation, which makes your program run faster. I put this slide in here because lots of people are talking about off-heap memory, and these are all the reasons why you'd be happier with a garbage collector than with off-heap memory. So what's the downside to garbage collection? It's pauses. You can imagine all your Java threads running, and then they hit a wall and they stop to do garbage collection. And there are various garbage collection algorithms in the JVM that run for various amounts of work that they do during those pauses. So the idea is that we want to shrink those pauses and make them less frequent. So why are we doing this now? Application requirements have changed. In 2000, when I worked in the GC research group at Sun, all of the our goals for the garbage collectors that are currently in the JVM were to have 200 megabyte heaps and pause times under 50 milliseconds. That worked great if you wanted to connect a phone call, but it's not working now in 2015, where we have these e-commerce applications with 100 gigabyte plus heaps, and they want pause times of less than 10 milliseconds. If you get a pause time longer than that, you might miss your stock trade window and lose $1 million. Or your customer might walk away from their shopping cart because they got distracted because it took too long. So that's why we now need lower pause time garbage collectors. So it's a silly graph, but what we want to do is we want to shrink the pause times. And we're going to do that by increasing concurrency. We're going to do more work while your Java program is running, so that we can do as little as possible while it's paused. So you forgive me this little bit of arrogance, but the idea is to try and slow down the Java threads as little as possible, and only when you absolutely have to. Before this, I used to work on a parallel programming language called Fortress, and there's a critical region, and you never, ever want to slow down the critical region in a parallel programming language. In a Java virtual machine, you never, ever want to slow down the Java threads of the JVM. So how is Shenandoah different? We still do the compaction of objects, but we do them while your program is running. So we're moving them out from under your Java threads because we're sneaky. So there are currently 4 garbage collectors available in the JVM, and I wanted to sort of set the stage for those to tell you where Shenandoah fits in. If you're running in a highly multi-tenant VM, say you've got 20 or 30 VMs running and you want a small footprint, minimal overhead, and you want a garbage collector that can vary with your program. So if you use a lot of memory and then a little, it'll give that memory back to the OS, you're going to want the serial GC. This is one that's kind of hidden, where there's a -XX : plus serial GC argument that you can use that will give you the minimal footprint. It uses a single GC thread, and it's a minimal footprint. If you want high throughput, if you want to calculate a fast Fourier transform or something else, and all you care about is from the time you hit enter to the time you get your answer, you're going to want the parallel GC. If what you want in the current environment is you want minimal pause times, you're going to want CMS. CMS doesn't do object compaction, so they can do their old generation collection while the program is running. The problem with that is they don't do compaction. So eventually your memory starts to look like a Swiss cheese, and you have all these little holes and no place to put this big object. And then G1. G1's goal is managed pause times. So they do compaction, a part of the old generation at each GC pause, but what you do is you say, I want to give you 50 milliseconds to do a GC pause. And G1 will go through and calculate how many old generation regions it can do in that 50 millisecond pause time. But they're still doing the compaction while the program is stopped. So what does Shenandoah do differently? We do our copying work while the Java threads are running. So our pause times are proportional to the size of your root set, not to how much actual GC work you have to do. So if you have a bazillion threads, it's going to be the time it takes us to scan those bazillion threads, but not to copy any objects. Our goal, holy crap, our goal was to have sub 10 millisecond pause times for 100 gigabyte plus heaps. We're not quite there yet, but we do have some SpecJBB numbers that we're pretty proud of. With a 140 gigabyte heap, comparing Shenandoah and G1, you'll see that we're only a little bit behind G1 on the max ops, but the critical JOPS, which is a measure of responsiveness, so within this 10 millisecond window or this 15 millisecond window, were you able to respond? We're getting basically twice as much. We're doing twice as well as G1. So if you look at our pauses, G1 for that run had 3,300 roughly pauses. We had under 900. If you look at the pause times, they spent 713 seconds in GC pause for SpecJBB2015. We spent 30. Their average pause time was 216, ours was 34. And their max was over 2,000, and our max was under 400. This large value, you see this 379 number, we fixed that today. I did these runs last weekend, and I just discovered that. So that's now down in the 30 millisecond range as well. All right, so we've seen varying results on different architectures. So we did the same run on an Intel Xeon box with 144 threads and a 350 gigabyte heap. Our max JOPS are worse than G1's by quite a bit, but our critical JOPS are still at least 50% better. So on a real benchmark, we're actually at that point where we've got our barriers in C2, and on a real benchmark, we're getting the kind of responsiveness that something like SpecJBB is looking for in critical JOPS. Again, I'm just putting up the pause times. They look very similar to the last ones. We're having, a third as many pauses. We're spending less than an order of magnitude in time. Not quite an order of magnitude less than our average pause times, and that max pause time has gotten better. If you were, watching and paying attention, you'll see we have an odd number of pauses. In fact, if we're in the middle of a concurrent cycle and we run out of space, we'll stop the concurrent cycle and do a full GC. And that's why we had an odd number. So how did we do it? This gives you a kind of a demonstration of what Shenandoah looks like. You have your Java threads running. They stop. We do an init mark. We scan all the threads. We start it up again and we do a concurrent mark while the Java program's running. We stop all the threads and do a final mark. This is to make sure that we've got an accurate view of what the heap looks like. And then we can start concurrent evacuation running while the Java threads are running. I showed 2 threads here, but we can run as many threads as you configure us to have. So the basic idea is that we've added an extra pointer to every object. So by using this, we can have all of our accesses go through that pointer. This means that the compiler and the garbage collector can agree at runtime on where an object lives. So if you wanted to do a read of an object, you look at that forwarding pointer and then you read the object from there. So here we have an object A that's been forwarded to the 2 region, and we can look at the copy that the garbage collector has made over here. If we go to do a read of B, it's still in a from region, and you can do reads from regions, that's fine. Writes will force a copy. So if you wanted to write to B, you're going to have to copy the object. The Java threads have to do this copying work. They copy the thread, and they install the forwarding pointer with a CAS. And then they perform their write. So everybody agrees on where the currently active copy of that object is. Pointer compare was a little tricky for us. It may force two copies. We were clever, and we do the pointer compare at first in the from regions, and if it succeeds, then we know they're the same object. It's only if there's a pointer compare and they fail that we have to do a copy to the to region of both A and B and make sure that we're comparing apples to apples. So what do our barriers look like? We've added a read barrier to every read, but it's a catch hit. And in the literature out there will show that this is less than 5%. And what we're seeing is even lower than that in terms of overhead for just the read barrier. So all we're doing is we're saying, okay, before you read the object, read the location above the object to get the current address of that object. And then do all of your pointer access or object accesses indirected through there. So the write barriers are heavier weight. They're actually a call out to the runtime system because they may require a copy. So for those, we check the evacuation in progress flag. And only if we are in the evacuation phase of that diagram I showed you before do we actually go through and do the write barrier. So read barriers are on things like get field or A loads, intrinsics. Write barriers are on things like put fields, A stores, intrinsics. I'm going to talk a little bit about how we implemented them. We spent the last year putting these barriers into C2. Putting them in the interpreter in the C1 was pretty much straightforward. But C2 has taken us the better part of a year. So if you think of a drag and book compiler with the front end that does all the parsing and the lexing and the tokenizing of your program, and then the middle end works on some sort of intermediate representation. That's what when I talk about C2, I'm talking about the intermediate representation. So if you took a compiler class in college, you probably learned about static single assignment. C2 works on something called a sea of nodes, which is sort of like a static single assignment. It has explicit memory controls, memory dependencies, and control dependencies that thread through the instructions that they use to make the optimizations. C2 was made to make both the generated code fast, but also, because it's a just-in-time compiler, the JIT itself has to be fast. So what we tried putting these in at parse time, like we did with C1 in the interpreter. And the problem was that a lot of the optimizations in C2 are looking for a particular set of intermediate representation instructions that they're pattern matching. And adding any instruction to that barrier, to that set of instructions, caused them to fail. We tried to do late barrier insertions, basically to trace things through all the optimizations that C2 does, and put the barriers in at the 11th hour. We couldn't get that to work. I'm not saying it's not doable. Probably somebody could get it done, but there's just two of us, and we couldn't make it work. We tried macro node barriers. If any of you have ever hacked C2, there's a notion of macro nodes, which is something you put in, and then you expand them right before code generation. And we tried that as well, but we still saw important loop optimizations that weren't getting done and were taking us forever. So our performance numbers were not where we wanted them to be. So what we did was we added two new nodes to C2. We added a read barrier node and a write barrier node. The compiler can see through these nodes. So if it comes through one of these nodes, it just assumes it's not there. We're not changing the control structure. We're not changing the memory dependency structure. We're only changing the control structure, and it allows a lot more optimizations. They can be inserted at parse time. And we can do Shenandoah specific optimizations on these barrier nodes. For example, if you have a newly allocated object, we know that that object is going to be allocated in two space. So we don't have to do any barriers on it. If we have a write barrier on a field in an object, any subsequent read barriers in that same method are going to be fine, and we can get rid of those. If we're reading two fields of an object, we don't have to do barriers on the second or any subsequent reads, because we know that we've already gotten the object in the right location. And we can hoist barriers out of hot paths like loops. This is tricky, and it took me a while to convince myself, as long as it's in the thread, in the frame, then even across the safe point, if there's a garbage collection that happens, that frame is going to get updated to point to the new stuff. So as long as it's in the frame, we don't have to have any read barrier or write barrier on it. So the current status, We're an official OpenJDK project. Yay! You can go to this URL. You can download our stuff. We have a repository there for JDK 8 and JDK 9. You can pull it down and play with it. We are stable, and we're getting performance numbers that we're proud of, that we're not embarrassed to talk about. So that's exciting. We're hoping to be able to get into the spring Fedora release. So what it will be is it will probably be like run, rather than saying Java, say Java Shenandoah, right? It's not going to be in the main bits, but it will be an option that you can load and play with. And it's always been our goal to get this put back upstream. And I don't have as much control over that because that's not Red Hat. But we're hoping that we'll get there and make a compelling case. So what are we still doing? Performance. There are some anomalies that crop up when we run new big applications that we need to understand. We need to get rid of all locks around allocation because the compiler takes a low-level lock and sometimes writes to Java objects, which can cause an allocation for a copy. And so that has to be completely lock-free because you're not allowed to take a lock while the compiler thread is running. We have some ideas for more C2 optimizations. We want to get rid of more barriers. We want to get that max JOPS number up. We need to do more big application testing. And we want you guys' help with this. If you have a big application that has, some performance numbers to come out, we'd love to run it. If you are doing stuff that's secret and you don't want to share your secret sauce, download our stuff and run it. Tell us whether we do well for your stuff. Tell us if we don't do well, why you think we're not doing well and what we need to do. We're trying it out on different architectures, and by that I mean both hardware architecture, well, by that I mean software. We're running on different hardware configurations to make sure we run well. But Red Hat also has like an AR64 architecture, and we're looking to maybe port to that and to try running this on something other than Intel 64. Right now, it's only x86 64-bit architectures that we run on. And there's heuristics tuning. I anticipate that to be huge, right? When do we start a concurrent mark? How many concurrent GC threads do we do? How many heap regions do we include in our collection set? There's a lot of tuning to go on. If you guys have been running G1, I was working on the G1 algorithm back in 2001. So it's almost 15 years of people playing with it and doing performance tuning on it. We have 2 guys, and in 2 years, this is where we are. We have a lot of low-hanging fruit as soon as we find it, I'm certain. And that's it. I'm a quick talker, but I'm happy to answer any questions.